So good afternoon everyone, Happy New Year, and we are very glad to start the seminar with a great talk by Marco Abadini from the University of Birmingham, who will tell us about coalgebraic flavor of metric compact Hausdorff spaces.
Yes, and yes, about this talk, it's going to be about compact metric spaces. Now, here a metric classically is defined as a function from the x times x for a set x to to 0 infinity, which satisfies four axioms like symmetry, self-distances are 0, separatedness, so distant points have positive distance, and triangle inequality. And an important class of metric spaces are compact metric spaces. These are the metric spaces that are compact in the topology that the metric induced. They are always compact Hausdorff spaces because every metric space is a Hausdorff. And the main example is 0, 1 to the n with a Euclidean distance. And now, in this talk, we're going to address a category of compact metric spaces. Well, the category of compact metric spaces and non-expansive maps has some bugs. Well, it's not great for some reasons that we will see. And the main point of this talk is just to see if we can tweak a bit the class of objects to get a good category of compact metric spaces, or a slight generalization of them. Okay, so what about this category of compact metric spaces and non-expansive maps is not so desirable? Well, first of all, it's not co-complete. Even two singletons do not have a co-product. And this is remedied by allowing distance infinite. This is fairly standard to do. And so now in this talk, a metric will be actually in this slightly more general sense, where we also include infinite as a possible value of a distance. Okay, and second problem, that this category of compact metric spaces and non-expansive maps is not complete. So if you take a two-element metric space, let's say with distance, for example, 1, then there is no countable power of this metric space. And the reason is that if I see that product metric, that is the sup metric, the uniform metric, this induces a topology which is not the product topology. There's this mismatch between the product metric and the product topology. And this topology is not compact. So in the end, this category is not complete. If we care about infinite products, we don't have them. And here the remedy is the following. Well, to have the topology and the metric just compatible, where the topology is not necessarily induced by the metric. That's the remedy to have to ensure completeness. And so in the end, instead of compact metric spaces, some researchers have defined these metric compact Hausdorff spaces. Specifically, this is a name given by Hoffman and Rice. A metric compact Hausdorff space X. Okay, not here that we have they've switched the compact and metric, so to emphasize that the topological part is not induced by the metric part. Okay, so a metric compact Hausdorff space X is a compact Hausdorff space X with a metric.
So again, here we allow the value infinite
that is lower semi-continuous. Now, lower semi-continuity means continuity with respect to the upper topology of zero infinity. What is this upper topology? Is generated by the upward closed open subsets of zero infinity. And it can also be expressed as follows. So if you take two elements, x0 and y0, the distance between them is less wrinkled than the limit when you approach x0 and y0 from a neighborhood. Okay. Yet another way to see this formula is the following. In words, let's say, if we have two elements and I'm interested in their distance, then small perturbation of these two elements may yield great increments, but not great decrements. Okay, so if I look close to them, then the distance maybe much higher, but not much lower. Okay. Yeah, as a side remark, the definition they actually gave consider a metric that does not require symmetry and separatedness, but in this talk we are going to assume that every metric is symmetric and separated. Okay. Let's see some examples. And for example, any compact metric space, any metric space whose topology induces compact is a metric compact Hausdorff space. Simply the topology is induced by the metric. Moreover, an example that is not of this form can be as follows. Take a compact Hausdorff space, for example, the interval 0, 1, and you say that you keep it with the Euclidean topology, and you say that every two distinct points have distance 1. Okay, this is still a metric compact Hausdorff space, and you can check that small perturbation that do not yield great decrements. Essentially because the only great decrement can occur when you identify 2 points. Okay, another example is the calm. For example, let's say we have this space here, and so on, with an accumulation line here. Okay, so here we have many. What's the name of these things? Many teeth, maybe. And here at the end we have an accumulation teeth. And if you keep it with a subspace topology induced by the inclusion into R2, and the metric that says, okay, if you want to go from here to here, you have to travel along the comb. So you have to consider how long this path here is, or if you want to go from here to here, you have to go this way. Also, this one is a metric compact Hausdorff space. You can see that again, small perturbations do not yield great decrements. For example, if I have a point here and a point here, and I perturb this, I point here on the border and I point here, and I move close to here, then the distance. Alright, actually, let's do like this. 2 points on this teeth in the border. If I perturb this a bit, then the distance increments a lot, but does not decrement a lot, because instead of going just like this, you have to go down and up. Okay, and finally, any product of compact metric spaces is a metric compact Hausdorff space. So if we keep it with the product metric and the product topology. So for example, if I take the unit interval and I consider all the function from a certain set I to 0, 1 with the product topology and the uniform metric, this will be a metric compact Hausdorff space. Do you have some questions? Okay. And in fact, this category is complete and co-complete. So the two problems about the category of compact metric spaces that I mentioned in the beginning here are resolved. And the purpose of our work with Hoffman is to show further good properties of this category. So in particular, we were wondering, okay, what about a well-behaved factorization system of this category? Okay, so regularity is a property about factorization of morphisms. Now here, if we look at most classes of algebras, such as groups, rings, and so on, we have a surjection, injection factorization. Surjective morphisms are also the regular APs and the strong APs. Injective morphisms are the monos, and surjective morphisms are stable under pullbacks. In fact, as you will know, if I have a class of algebras closed under arbitrary products and subalgebras, this is a regular category. Yeah, probably there's no need to recall the definition of regularity. But anyway, we have it written here. We have a strong AP monofactorization, and this factorization is stable under taking pullback. That is, if I have a pullback of a strong AP, this is still a strong AP. Okay, and well, if my class of algebras is very well behaved, that is closed under also homomorphic images, then we have bar exactness. And okay, but there are categories which are not regular. For example, the category of topological spaces, although they have let's say factorization systems. So for example, a continuous function has different factorizations as a surjection, injection, surjection followed by an injection, depending on what topology you put on f of x. And here there are two extreme cases. The extreme cases are, okay, if we keep f of x with the topology, the quotient topology induced by x. In this case, we have a strong AP monofactorization. Okay, so here, this topology is induced by here, and this injection is not in general an embedding, but it's just an injective continuous function. Or we can do the other way, keep f of x with a subspace topology induced by y, and this gives an AP strong monofactorization. And in fact, in a certain sense, this is better behaved than this factorization. Why? Well, strong APs are not stable under pullbacks. Okay. And therefore, the category of topological spaces is not regular. So in a certain sense, this factorization is not so ideal from the point of view of regularity. On the other hand, top is co-regular, so the opposite is regular. And this means that co-regularity of top means that strong monos are stable under push-outs. So these embeddings are stable under push-outs. And that makes top a co-regular category. Here we just dualize the definition of regularity. So this means that every morphism has an epi-strong mono factorization. And the push-out of a strong mono along any morphism is a strong mono. Okay. So maybe as a very rough way of understanding regularity, I have this picture in mind that if I have an embedding x into y and a morphism from x to x prime, then we can replace inside y instead of x, we can replace x prime and get a new structure where x prime is embedded. We'll see an example with these metric compact Howell spaces. Okay. So this is the rough rule of thumb that we can test. That categories of algebras are regular and maybe even bar exact in certain cases, while category of spaces are co-regular and maybe even bar co-exact. In this rule of thumb, the metric compact Howell spaces fall in the second categories, and we'll see how. So just to recap, we were interested in these compact metric spaces, and we've seen that this category lacks some fundamental interesting properties. So we got interested into a certain class, a certain generalization called the metric compact Howell spaces, and now we're going to show that indeed has various good properties, not just complete and bar exactness, but also a good factorization in this second sense, like co-regularity. Okay. So in fact, if I have a morphism of metric compact Howell spaces, recall that a morphism is a function that preserves the metric and the topological structure, namely a non-expansive continuous map. And then we can factorize it as follows. You equip the image with the metric and the topology induced by y, and you get an epi-strong mono factorization. In fact, we prove that surjective morphisms are precisely the epimorphisms, and embeddings are precisely the strong monos and regular monos. Okay, and we proved that this category is indeed co-regular, so that embeddings, which are the same things as strong monos, are stable under push-outs. And yes, just to get an intuition about how this push-out look like, I have a main example with of a push-out. So let's take map of Italy, where I come from. Okay, and in Italy, let's say we are many years ago, where the only way to travel from a point to another point is by walking. Okay, and there are three places called Milan, Rome, and Naples. And here the traveling distances are, for example, if you want to walk from Milan to Rome, then you're going to take 138 hours. If you want to go from Rome to Naples, 51. If you want to go from Milan to Naples, yeah, slightly less than some 184. Okay, and let's suppose that now we have a huge improvement in technology and a new and a train connection is built from Milan to Rome, which now takes 3 hours. Okay. And yeah, here we're assuming distances is measured in hours. Okay, now this changes the metric of Italy, right? Now, from Milan to Rome, the distance is 3 hours. Well, from Rome to Naples, the distance would still be 15 hours, because you will not take the train to Milan to go to Naples from Rome. But the distance from Milan to Naples also will change. It will be, well, you take the train 3 hours, then 51, it will be 54 hours.
Here you are adding. The other one was not the same.
Yes, because because if you walk, then from Milan to Naples, then there's no need to pass by Rome.
There is an alternative.
Oh yes.
I thought the whole roads go to Rome.
Oh, right, exactly. Exactly. Well, unfortunately, we have a counterexample. Yeah, here the metric was just a walking distance.
Just
yes. Exactly. Okay, so, and this is essentially a push out. How? So, okay, here we have the old map of Italy. I'm copying it with the distances, with the regional distances. So here it's 138, and then here I write the new, well, Italy with the new metric, which, for example, takes you 3 hours to go from Milan to Rome, and so on, and 54 from Milan to Naples. Okay, what are we doing? Well, we're taking the subspace consisting of two elements, consisting of just Milan and Rome, which has distance 134.8. This is embedded into Italy. And now, here we are taking a new space consisting of two elements, the train line, if you want, from Milan to Rome, with distance 3. And what we do, we consider the assignment that assigns to Milan this point, to Rome this point. This is a morphism because it's fortunately by going by train takes you less than walking, so it's not expansive. And if you do the push out, then we get precisely this new map. So in a certain sense, these push out are okay. Take your big space, and instead of your subspace, you replace it with this new space. And if you see here, this is embedded from here because in this new metric, going from Milan to Rome will take you 3 hours as here. Thanks to the fact that this was a morphism, so an expansive map. Okay, and here, blue for Italy. Okay. Yes, and in general, okay. So, yes, this was an example just to have a way to see how push-outs work. And so these embeddings are stable under these push-outs. And in fact, we have even more, that this category is Barco-exact. Okay, again, here to have an intuition, we can say, roughly speaking, that Barco-exactness means the following. If I have an object x and a surjective morphism going from x plus x to another object. If this satisfies certain properties, reflexivity, symmetry, transitive, then actually there is a, let's say I have x, two copies of x, then let's say this is x, and these are my two copies. Then there is a subspace A such that my morphism from x plus x to z is obtained by actually identifying for each element in A the two copies here. So I'm gluing by identifying each two copies of the same element. Okay. This is essentially what Barak coexactness says. I will go a bit into more details to sketch the proof of this theorem, what exactly reflexivity, symmetry, and transitivity means. This is just to have an idea what kind of things Barak coexactness means in this setting. Okay, the key for this is encoding surjective morphisms. So here we have a surjective morphism from x plus x to z. Well, actually we'll be interested in isomorphism classes. So if we have another surjection to another object, but these are isomorphic, then this would be in the same isomorphism class. And so we're not very much interested into the set-theoretic structure of Z. And so the idea is to encode it, an isomorphism class, internally in X, as follows. If I have a surjective morphism, let's do it more in general, not just from two copies of the same space, but from space X to Y. Then the isomorphism class of this surjective morphism going out of X can be encoded just by saying, just by a function from x times x to 0 infinity that tells you, okay, give me two elements, x1, x2, and I will tell you what is the distance between the two images of the images between the two elements. Okay, and from this you can recover what is y and what is the function. Essentially, because to get y back, it will be a partition of x. You just identify the elements that where this gamma f is 0. Then to get the topology on y will be the quotient topology of x. That's because every continuous function between compact outer spaces will be a quotient. And the metric, well, will be suggested by this function. So, okay. And okay, and what are the characteristic properties of such a function? So when we have a function from x times x to 0 infinity, when do we know that it arises from a surjective morphism? Well, there are two properties. One, that it is a premetric. So this means that it has all the properties of a metric except for the fact that two different points may have distance 0. So we call it premetric. And second property is that since the morphism is non-expansive, then this gamma should be below the metric on x. So gamma of x1, x2 should be less or equal than the distance from x1 to x2 in x. This comes from the fact that it should encode a non-expansive map. And so we say that it's a sub-premetric of x. Second properties, since we want f to be continuous, since we want y to have a metric that is lower semi-continuous, also this gamma f should be lower semi-continuous. If you have some questions, was it a question?
Yeah, maybe one.
Sorry?
So if you have a pre-metric,
Yes.
you can always start from it metric, right? Metric in your sense. So a lower semi-continuous metric. You just identify
Yes, exactly.
things that are below. Well, yes, that are bounded by D. But
Oh, can you repeat the question, please? If you
I was still thinking, so maybe it's not a really a question, but I was trying to figure out if the fact of having a pre-metric was enough to then have a metric on Y.
If you have a pre-metric, is this enough to have a metric on y? So if you have a pre-metric without necessarily being below, or
Yes. So if you have a pre-metric, if you have a pre-metric on X,
yes,
you can always build a quotient where you have a metric on
yes,
X module is pre-metric.
yes, exactly. Yes, there's no need for this. You can always have a quotient. Yes. Well, you identify elements that have distance 0. But if you want this to be a morphism, so a non-expansive map, then you add this requirement that is below dx. But was it worse? You have a question?
No, I was wondering if you really need. Yes, okay, I see what it was. Never mind.
Or your question was, well, then I can, if I have a general pre-metric, then I can make it, then I can tweak it so that it becomes below dx. No, maybe.
Actually, I don't know. I think like, I think you have a pre-metric, you move the quotient there.
Yeah.
You make it a metric. You also have the lower simultaneous property.
Yeah.
It is preserved even if you don't have a bound.
Oh.
But I think the thing is that that quotient would then be non-expansive with respect to the pre-metric on X, but not with the existing metric necessarily.
Yes, yeah. What you're saying is correct. Yes, if we don't require belowness, then we get a metric. The morphism will not be non-expansive with respect to the existing metric on X. It will be non-expansive with respect to this gamma. And and symmetry. Sorry. And I don't know whether probably for also without this condition belowness, if you have a lower semi-continuous pre-metric, then the metric you get on Y will be lower semi-continuous. I guess it will be the case. Any more questions? No more questions? Okay. And so yes, the isomorphism classes of surjective morphisms out of an object X are in bijective correspondence with the lower semi-continuous subpremetrics on X. Okay. Yes. So I'm not sure whether this encoding is clear. It seems so, but let me just give an example. So for example, if I have a 3-element space, let's say, let's say distance 1, this distance 1, and this distance 2, and I quotient it maybe by identifying these two elements here, and let's say that this distance is 1/2, then the sub-free metric on here will say, okay, these two elements have distance. These two elements have distance 0, because here they have distance 0. These two elements, the sub-free metric will be 1/2, and from here to here, it will be 1/2 because the image is 1/2. And yes, and if we forget for a second here, and we just remember these distances, then we get back the morphism because we say, oh, these have distance 0, so let's identify them. And then these points become, okay, from here to here we have distance 1/2, because that's the distance prescribed. Okay. Okay, so finally, Barkhoff exactness. Barkhoff exactness means that every internal equivalence correlation is a cokernel pair. Okay. So what is a cokernel pair? Okay, let's see what is a cokernel pair of embeddings. This is enough. If I have an embedding, let's say of A into X, then maybe here. Okay, I have my space X. I'm not sure if you can see it from there. You can? Okay, and I have my subspace A. Okay. Well, I can take 2 copies of this, and I can quotient these 2 copies by identifying 2 elements, 2 copies of the same element in A. Actually, just as I did there. This is the cokernel pair of an embedding. You can see it either as a map from X plus X to something, or as 2 maps from X to this quotient here. And now Barkhoff exactness will say that if I have an internal equivalence correlation, it would be an identification of this type. And here, it's good. It was handy for us to, instead of working with quotient maps, to work with associated lower stability continuous sub-free metric. Okay. Which will be. So first of all, what is an internal binary correlation? This will be an internal binary correlation on X. If I have my space X here, then I take 2 copies of these, and an internal binary correlation would be a surjective morphism from here to some objects, but we can think of this as a lower semi-continuous sub-free metric on here. So essentially we are saying, given 2 elements in this joint union, what is their distance? Where their distance means actually the distance when we quotient. Okay, let's go. So let's say let's call this distance gamma. And then if you look at the axioms of reflexive, symmetric, and transitive, we can turn this into concrete hypothesis, concrete properties on gamma. So, for example, what is reflexivity? Well, a binary relation is reflexive if there's a morphism from X to R that makes this diagram commute, where here we have a diagonal and here we have our relation. Dually reflexive correlation means that there exists a relation, a morphism from my quotient R to, well, this is a codiagonal. And essentially, the fact that this is a morphism so any morphism is non-expansive, it's a non-expansive map. And so it will mean that the distance calculated here is greater or equal than the distance calculated here. Okay, and so this will give the following condition. Whenever I take two elements, x and y, okay, here I'm denoting an element. If I have an element x here, I will denote by x0 the first component, and x1 the second one. Reflexivity means that if I take two elements xy and I take let's say x0 and, for example, y1, I can take x1 or here y0, the distance between the two concerning gamma, the gamma distance is is greater or equal than the distance in the space between x and y. Okay, and by the way, if I have something reflexive, then if I look at the distance of two elements in the same copy, this will be precisely the original distance here, because this gamma is a subperimetric, so it's below the distance that this x plus x has. And okay, then we can translate symmetry. Symmetry says the distance between 2 points here, the gamma distance is the same as the distance if we swap coordinates. This here. Oh no, and transitivity instead says transitivity under reflexivity and symmetry says if you want to calculate gamma from, let's say, x0 to y1, if this is not infinite, then there exists some point z such that this distance is the same as the sum of the distance from x0 to z1 plus the distance from z0 to y1. Okay, so gamma of x0, y1 is the sum of these two things. Okay, and now bar coexactness says that actually this z essentially says that this z can be chosen so that the gamma distance between these two copies of z is 0. Okay, so yeah, that's essentially what it says. Or this is equivalent. The distance between these and these is the same as the sum of the distance from x to z and z to y. This essentially means, oh look, actually going from here to here is the same as going from here to here. And then, well, you have these seem identified, so I jump here without any cost, and then I go from here to here. And here, to find this Z, compactness is crucial. Okay. In a certain sense, well, this was a rough sketch of the proof that this category of metric compact Harlow space is Barkov exactness. It's Barkov exact. And so, okay. To sum up, if you allow infinite measures and the topology not to be induced by the metric, then we have some good categorical properties. So we have that this category is complete, co-complete, and Barkov exact. And we have some open questions. So now completeness, co-completeness, and bar exactness are some of the main properties of varieties of algebras, so equationally defined classes of algebras. So the question, actually probably the motivating question for our work at the beginning was this, and it's still open. Is this category dually equivalent to a variety of possibly infinitary algebras? What's left to verify is whether there is a regular injective regular cogenerator. We don't know. And probably, if there is, then the variety that is dual to this will be of infinitary algebras. One more questions that came up when I was preparing this talk is, okay, well, requiring the compact Hausdorff topology to be induced by the metric makes us lose infinite products. And actually, this was we said, okay, no, we want infinite products, essentially because we were trying to understand whether this whether MET-CH is dually equivalent to a variety of algebras, and all varieties are complete and co-complete. But maybe one is not interested in infinite products, just cares about finite ones. So the question is, well, if we require the compact Hausdorff topology to be induced by the metric, do we still get this finitely co-complete, finitely complete, and Barkov exact category? Will the proofs go through? This will be interesting because it will be more close to what is usually done when studying metric spaces. And moreover, as last question, for those who know about quantiles, this work we used zero infinite as a quantile, but it can be substituted. I mean, the same questions can be addressed for other quantiles. For example, in my PhD thesis, I proved that essentially, if you replace this by the two-element quantile, 0 of 1, then, well, the category that you get instead of this MET-CH, which is the category of Nachman's compact orbit spaces, is dually equivalent to a variety of algebras. In particular, it's Barkov exact. It was already proved that it was dually equivalent to a quasi-variety of possibly infinitary algebras. And but one can investigate whether other quantiles still give you Barkov exact categories. C'est tout. Merci pour votre attention.